used to think friction was this magic thing stuff, and then I've learned, guess what? It comes down to what I tell my physics students. It's bumpies. It's the bumpies between two surfaces. Okay? We've got this crate sitting on a floor, right? If we zoom in, and that's what this little zoom in picture is. If we zoom in, friction is just the interaction between those two surfaces. Right? All right. How many of you played with sandpaper or use sandpaper? Yeah. Well, you know that sandpaper comes in different roughnesses. It's called grit. Okay? 80, the lower the number, the more rough the sandpaper is. So 80 grit is really, really rough. 100 grit's a little less rough. 120 is less rough. 180 is less rough. You can get up to 200, 500, 1,000 grit sandpaper. And it starts getting very, very, very smooth. Okay? But if you take 80 grit sandpaper, oh wow, look, check this out. I got 60 grit. So very rough. Okay? Very rough, very rough. If I got 60 grit over 60 grit, guess what? I got lots and lots of friction here. Okay? That would be a lot of friction. But you can go to the other end of the scale. Think about a melting ice cube sitting on a melting ice cube. There's almost no friction. So it's all a function of how much the bumpies on each surface are interacting. That's where friction comes from. So how many of you have had to move a big heavy object? Okay, right? So what happens? You push on it, you push on it, you push on it, and then finally it moves, right? Well, that gives us a clue, and we've experienced that there's actually two types of friction. There's one called static friction, okay? And that's friction that opposes the start of motion. And then you've got this stuff called kinetic friction, which is the friction that resists motion once it's started moving. Okay? And the static is always bigger than kinetic. That's why we've experienced that where you've got that heavy dresser or whatever it is, and you have to lean into it and you push on it and you push, and then finally it breaks free, and it's a whole lot easier to keep it moving than it was to get it started. All right, so let me back up to this picture, okay? All right, big heavy object, we push on it, eventually we get it moving. It's a whole lot easier to keep it moving than it is to start it moving. So the amount of force, okay, the amount of friction that it takes before we can get it moving is called static, because static means it's sitting still, it's not moving. And then kinetic refers to motion. Kinetic friction is the friction that it experiences once it is moving. And so this little symbol here in the middle, Fs, so friction, the little subscript S would be static friction is always greater than kinetic friction. That's why it's harder to get it moving than it is to keep it moving. Okay? Now, also, guess what? We talked about free fall last lesson. That air resistance, remember when we didn't have the vacuum in the chamber, we had air in that? That air resistance actually is a form of friction. And in fact, there's an equation that we can actually figure out how much that friction is. And no, this is not testable. It's more of just making you aware that it's out there. But an interesting thing happens, okay, when something's in free fall and you've got air resistance. There comes a point where the friction that we call air resistance or drag balances out the force of gravity, our weight pulling us down. And that is called terminal velocity. Anybody ever been parachuting? Okay, I've done this. Yes, this is a picture of me over Galveston, Texas, falling through the sky towards the earth at terminal velocity, which is around 120 miles per hour. If you ever get the chance to do it, I would highly recommend go and do it. It's such an amazing experience to be falling through the air. I've done it 6 times. So my number of takeoffs, right, and my number of landings are off by a count of 6. When I was a cadet at the Air Force Academy, they had a program called Airborne or Free Fall, where we actually got to throw our own bodies out of the airplane and pull our own ripcord and safely bring ourselves to the ground. That picture of me that I just showed you, that was done in tandem. Okay, that's me strapped to another guy in a double harness. It's still a lot of fun. All righty. Now, if we get rid of air, guess what? There is no friction. So out in space, there is no friction. And so Voyager 1 and Voyager 2, which were launched in 1977, have experienced true no friction. And they have actually left our solar system. As far as we know, they are the first interstellar space vehicles. Take a look at this picture. Okay. This thing called the heliosphere. That's kind of the outer boundary of our solar system. Let me kind of change the view up on you here a little bit. So we got the sun in the middle. Okay.
Professor, a question. Are the V'gers still accelerating? Like, since they have no friction, do they perpetually keep accelerating and going faster and faster?
Let me think about that for a second. So, in one sense, there's nothing to slow them down, but they're also not near anything, any other objects that have a large amount of mass that would cause a force of gravity that would accelerate them. Now, there may be other smaller objects, so there's probably some balance. It's probably not a constant acceleration. Okay, again, because they're out there and there's not a lot, there's not like another planet or another star or something out there that's going to put a gravitational force on it. But they themselves do have mass, and so they're going to have inertia to continue carrying on. So that's a great question. I would have to think about that some more. How's that for a nice vague answer, George?
Nice. I like that. It was a faith-based question. That's what I tell the kids. You're asking a faith-based question.
Well, you know, I tried. Hopefully, you heard me thinking out loud there. You know, because mostly, when we've got, whether it's the Mars lander or the Voyagers or whatever, we end up using the gravitational force of different planets or things like that to our advantage to either speed things up or slow things down. But now that they're out past, the orbit of Pluto and that, and outside the our solar system, there's not much out there that's going to have enough mass to accelerate it. But as we just discussed, there's also in essence, no friction to slow it down. So I'm thinking it's probably at some speed, some velocity, probably remain at a constant velocity because there's nothing out there to, create a force to accelerate it. So it's probably at a constant speed. Anyway, I don't know if you guys have seen this. This is kind of fun. Voyager 2, they the Voyager 1 and Voyager 2 actually each took a different path through our solar system. And in 2012, one of them left our solar system. And in 2018, the other one left. And this is kind of a fun little historical view of some of that.